Welcome to another episode. Wherever you are, take a moment to settle in. Maybe you're lying down, letting your day fade away, or maybe you're simply drifting with headphones in, curious about what you'll hear tonight. I'd love to know where you're listening from and what time it is where you are. So if you'd like, leave a comment and share that with me. And if this kind of journey through science, history, and wonder is something you enjoy, consider subscribing so you can drift with me again next time. Tonight, we're going somewhere that most of us will never see with our own eyes, yet it makes up the vast majority of our planet. Not outer space, not a distant star system, but something much closer: the deep sea. When we think of exploration, our minds often drift upward, to the moon, to Mars, to galaxies far away. And yet, beneath the surface of our own oceans lies a realm that is, in many ways, even less familiar. A realm of extremes, of lightless voids, unimaginable pressures, strange creatures, and alien landscapes. The deep sea is not just a place on Earth. It is Earth's last great frontier. Scientists estimate that over 80% of the ocean remains unexplored, unobserved, and unmapped. To put that in perspective, we know more about the surface of Mars than we do about our own seafloor. The irony is almost humorous. We build telescopes to peer billions of light years into the past, but most of us have no idea what lies just a few kilometers or a few miles beneath our feet under the waves. The ocean is vast. Covering over 70% of the Earth's surface, it contains nearly 1.35 billion cubic kilometers of water. That's about 324 million cubic miles. If you could somehow scoop it all into a sphere, that sphere would be more than 1,300 kilometers across, about 800 miles. That's wider than the distance from Paris to Rome, or from New York City to Chicago. And yet, if you stand at the shore, looking out at the horizon, it feels deceptively flat. We think of the sea as a surface, a calm sheet stretching outward. But in reality, it is depth, unfathomable depth. The deepest part of the ocean, the Mariana Trench, reaches almost 11,000 meters, around 36,000 feet, or nearly 7 miles. If you dropped Mount Everest, which rises 8,849 meters, or 29,032 feet, about 5.5 miles, into it, the peak would still be more than 2,000 meters, about 6,800 feet, or over a mile, underwater. Imagine that for a moment, the tallest mountain on Earth, completely swallowed by water, with room to spare. And in those depths, in the crushing silence, life exists. Not just life, but an entire hidden biosphere, teeming with organisms so bizarre that they seem more like the inventions of a science fiction writer than real earthly creatures. Fish with transparent heads, shrimp that spit glowing sparks, worms taller than a man, some more than 2.4 meters long, or about 8 feet, yet with no mouth and no stomach. To begin, though, let's pause on the threshold of this abyss. Picture the journey. At the surface, everything feels familiar. Sunlight dances on waves, boats skim across, gulls wheel above. Just below the surface, you might find schools of fish flashing silver in the light, or coral reefs bursting with color. This is the world we know: shallow seas, coastal shallows, places where humans can swim and dive. But descend just a little, and things begin to change. At about 200 meters, roughly 660 feet, the sunlight fades. This region is called the twilight zone, or mesopelagic. Here, light dwindles into dim blue shadows. Colors drain away. Human eyes would see little more than a permanent dusk. Go deeper still, past 1,000 meters, about 3,300 feet, and the midnight zone begins. No sunlight penetrates here. It is perpetual night. And yet, paradoxically, this is the realm of light, not from the sun, but from life itself. Creatures here make their own glow, bioluminescence, painting the blackness with blue-green sparks, pulses, and flares. Tiny plankton blink like stars. Predators dangle glowing lures. Squid flare up with bursts of light to startle attackers. It is a galaxy beneath the waves, a cosmos of living constellations. And below that, the abyss. At depths of 4,000 meters or more, over 13,000 feet, the pressure is so intense that a human body would be crushed instantly. Temperatures hover just above freezing, about 2 to 4 degrees Celsius, or 35 to 39 degrees Fahrenheit. And yet, life persists. Strange, delicate, impossible life. The word abyss comes from the Greek abyssus, meaning without bottom. It carries a weight of myth and fear, the unknowable void. And standing on the shore, looking out, we are gazing at that very abyss. Philosophers have often used the sea as a metaphor for the unconscious. Carl Jung once compared the depths of the psyche to the ocean, dark, vast, teeming with unknown forces, occasionally surfacing in dreams. The deep sea, in a way, is our planet's unconscious mind. It hides its secrets from us, occasionally offering glimpses in the form of a strange, washed-up creature, or a deep-sea submersible's fleeting footage. But the rest remains out of reach, waiting. It's easy to forget how recent our exploration of the abyss really is. For thousands of years, humans assumed that life could not exist at great depth. Aristotle wrote about marine animals, but only those near the surface. In the 19th century, many scientists still believed that below about 600 meters, around 2,000 feet, the ocean was barren. They called it the azoic zone, the lifeless zone. It wasn't until the mid-1800s, when deep-sea dredging expeditions began hauling up living creatures from the depths, that this assumption was shattered. It was like discovering an alien civilization living beneath your feet. And the deeper we looked, the stranger things became. Tonight, we'll wander into this world. We'll drift slowly, like a submersible lowering its lights into blackness. We'll meet creatures with jaws that unhinge like nightmares, and others that look almost comical in their strangeness. We'll explore vents that gush black smoke hotter than molten lava, yet provide life to vast colonies of worms and crabs. We'll see how evolution has played with form and function in ways that seem impossible, as if the deep sea is nature's hidden workshop, where rules bend and imagination runs wild. And as we do, maybe we'll reflect on what this hidden world tells us about life, about resilience, and about the limits of human knowledge. So close your eyes if you'd like, and picture it. The descent begins. The surface world fades behind you. The sound of waves, the gleam of sunlight. You sink into blue, then into black. Pressure builds, silence deepens. And ahead, in the eternal night, faint glimmers of living light appear, like distant stars guiding you into another universe. The abyss awaits. As we begin our slow descent into the abyss, it's worth remembering that for most of human history, no one truly knew what was down there. The ocean's surface was both a highway and a horizon, something to travel across, not into. The deep sea was not a place to visit. It was a mystery to fear. In ancient times, the sea was a realm of gods and monsters. The Greeks imagined Oceanus, a vast river encircling the world, and Poseidon, whose moods could raise storms or calm the waves. Sailors told stories of krakens, serpents, and great beasts that lived in the dark below. For millennia, the deep was not a physical frontier. It was a mythological one. And yet, even in those early centuries, there were those who tried to understand it. Aristotle, writing around the 4th century BCE, made some of the first recorded observations of marine life. He studied cuttlefish and starfish and described the organs of fish and mollusks with surprising accuracy. But his knowledge, like that of all ancient scholars, was limited to what could be caught near the shore or in shallow nets. Beyond a few dozen meters, perhaps 30 or 40 meters, 100 to 130 feet, the sea became unreachable. For centuries, the ocean floor was imagined as a dead, featureless desert. Even after the Renaissance brought new instruments and a hunger for knowledge, the deep remained hidden. Early divers, using crude wooden helmets and air pumped through tubes, could reach only a few tens of meters. By the early 19th century, the record for human depth was about 60 meters, around 200 feet, before pressure and lack of air forced divers back. Still, curiosity persisted. The first real glimpses of the deep came not from divers, but from ropes and hooks. Scientists began lowering weighted lines into the sea to measure its depth. This process, called sounding, was slow and unreliable. In 1854, the US Navy used it to measure the Atlantic and discovered an unexpected plateau between Europe and America, what would later be called the Mid-Atlantic Ridge. That same year, telegraph companies became interested. If they could lay a cable along that ridge, they could connect continents. Technology once again became curiosity's partner. But the true birth of deep-sea science, what we now call oceanography, began with one grand voyage, the HMS Challenger expedition. In 1872, the British Royal Society and the Royal Navy launched a mission unlike any before. The Challenger was a converted warship, stripped of most of its guns, and loaded instead with laboratories, microscopes, thermometers, and 291 kilometers, 181 miles, of hemp rope for deep-sea sampling. Over the next 4 years, it would sail more than 125,000 kilometers, over 68,000 nautical miles, across the globe, taking thousands of measurements and dredging the ocean floor. The scientists on board faced conditions that were, in every sense, extreme. Sounding lines sometimes took hours to reach the bottom. The ropes twisted, snapped, or tangled in storms. The crew battled rough seas, diseases, and exhaustion. But when the samples finally came up from depths of 4,000 to 8,000 meters, 13,000 to 26,000 feet, what they found astonished the world. Life. Tiny, fragile, alien-looking life forms, corals, sea cucumbers, brittle stars, all living in total darkness. The discovery shattered the azoic hypothesis, the 19th century belief that life could not exist below 600 meters, about 2,000 feet. It turned out that not only could life survive there, it flourished. The Challenger crew catalogued over 4,700 new species, measured ocean temperatures at various depths, and confirmed that the seafloor was not flat but shaped by trenches, ridges, and basins. It was a revolution. Their data filled 50 volumes of reports, more than 29,000 pages of observations and illustrations. Modern oceanography was born aboard that ship. One of their greatest discoveries was a deep trench in the western Pacific, near the Mariana Islands, a name that would echo through history, the Mariana Trench. At the time, their crude sounding line measured it at around 8,200 meters, 26,900 feet, already unimaginably deep. Later, better instruments would reveal the true figure, nearly 11,000 meters, 36,000 feet. But the question that haunted scientists for the next century was simple. Could we ever see it with our own eyes? By the early 20th century, engineers began to dream of machines that could take humans where the body could not go. Pressure at a depth of 10,000 meters is over 1,000 times greater than at the surface, equivalent to the weight of 50 jumbo jets pressing down on a single human body. Yet inventors were undeterred. One of the first major breakthroughs came in 1930 when an American engineer, Otis Barton, and a naturalist, William Beebe, created the bathysphere, a spherical steel capsule about 1.5 meters wide, roughly 5 feet. It had quartz windows and was lowered on a steel cable from a ship. Beebe and Barton descended off Bermuda to a record depth of 923 meters, 3,028 feet. They described seeing bioluminescent creatures, jellyfish that glowed like lanterns, and fish with phosphorescent eyes. The bathysphere was primitive and terrifying. It had no propulsion, no control, only a phone line and a cable holding it above the abyss. If that cable snapped, there was no rescue. The risk was unimaginable, and yet they went again and again, driven by wonder. Beebe later said, "Half the pleasure of the deep sea dive was the delicious terror of it." By the mid-20th century, science pushed deeper still. In 1960, a Swiss oceanographer, Jacques Picard, and a U.S. Navy lieutenant, Don Walsh, boarded the bathyscaphe Trieste, a submersible that looked more like a steel balloon than a submarine. It carried a crew sphere filled with gasoline for buoyancy, and ballast that could be dropped to ascend. On January 23, 1960, they descended into the Challenger Deep, the very bottom of the Mariana Trench. At 10,911 meters, 35,797 feet, they became the first humans to reach the deepest known point on Earth. The descent took nearly 5 hours. The pressure outside was over 1,100 atmospheres, more than 16,000 pounds per square inch. At one point, they heard a loud crack. The outer window had fractured under stress, but they continued. At the bottom, they saw a flat, light-colored seabed. And then, something moved. A small, flat, fish-like creature swam past. The existence of life at that depth stunned biologists. After 20 minutes on the bottom, they released their ballast and began the long ascent back to the surface. When they emerged, the world greeted them as heroes, explorers of an inner space. It would be more than half a century before another human returned to those depths. The next major leap came not from military programs, but from scientific research. In 1964, the United States built Alvin, a small manned submersible capable of reaching 4,500 meters, about 15,000 feet. Compact and maneuverable, Alvin became the workhorse of ocean exploration. In 1966, it recovered a lost hydrogen bomb off the coast of Spain. In 1974, it explored deep coral reefs in the Bahamas. And in 1977, it made one of the most important scientific discoveries of the 20th century: hydrothermal vents near the Galapagos Rift, where entire ecosystems thrived without sunlight. That single dive changed biology forever. Until then, scientists believed that all life ultimately depended on the sun. But around those vents, at depths of 2,500 meters, 8,200 feet, Alvin's cameras revealed giant tube worms, clams, and crabs living in total darkness. They survived on energy from chemicals, not sunlight, hydrogen sulfide from the vents, used by bacteria in a process called chemosynthesis. It was the discovery of a new kind of ecosystem, independent from photosynthesis, and possibly a clue to how life began on Earth. From Aristotle's sketches of shallow fish to Alvin's glowing lamps illuminating the abyss, the journey had taken over 2,000 years. Each generation looked a little deeper, pushed a little further. And with each descent, humanity's view of its own planet changed. But exploration is never just about technology. It's about human nature, our restless need to know. When you read the diaries of those early explorers, what stands out isn't just the data or the discoveries. It's the awe, the humility, the sense of standing before something incomprehensibly vast. The ocean humbles us in a way few other things can. Even today, in the age of satellites and supercomputers, more than 80% of it remains unmapped. We've sent rovers across Mars, but we've mapped less than a quarter of our own seafloor. The reason is simple: the deep ocean doesn't want to be explored. It resists us. The cold, the darkness, the crushing pressure, everything about it tells us to stay away. But curiosity is stubborn. That's why in 2012, filmmaker James Cameron, yes, the same one behind Titanic and Avatar, built a submersible of his own called the Deep Sea Challenger and descended solo to the bottom of the Mariana Trench. He stayed there for nearly 3 hours, collecting samples and filming in 3D. He described the seafloor as a desolate lunar plain, silent and alien. The first solo human to reach Earth's deepest point wasn't a Navy officer or a scientist. It was an artist driven by wonder. From myth to measurement, from rope lines to titanium hulls, the story of deep-sea exploration is the story of curiosity triumphing over fear. And maybe that's what makes the deep so magnetic. It's not just what we find there. It's what it says about us. Humanity has always been drawn to the edges of the map, to the places marked unknown. We build machines, risk our lives, and defy nature's limits, not because we have to, but because we can't stand not knowing. The ocean remains, even now, our mirror in darkness, reflecting both our ignorance and our imagination. And as we drift deeper into this episode, we'll begin to meet the inhabitants of this world, the creatures that thrive in pressure, cold, and eternal night. But before we meet them, it's worth pausing to consider what it takes to live under such conditions, how life, against all odds, endures where it shouldn't. Let's keep descending. As our descent continues, the world above fades into a memory. Sunlight has long vanished. The weight of the ocean grows heavier, layer by layer, as we drift into the deep. The pressure here isn't something you can truly imagine. It's a kind of invisible gravity, a constant, relentless squeeze from every direction. At the surface, we live under one atmosphere of pressure, roughly 101,325 pascals, or about 14.7 pounds per square inch. It's so familiar we never notice it. But for every 10 meters, about 33 feet, that you descend beneath the surface, the pressure increases by another atmosphere. At 100 meters, 330 feet, it's 10 times greater than on land. By 1,000 meters, 3,300 feet, it's 100 times greater. And at the bottom of the Mariana Trench, nearly 11,000 meters, 36,000 feet down, the pressure is more than 1,100 atmospheres, over 16,000 pounds per square inch, equivalent to the weight of 50 jumbo jets pressing down on a single human body. A human at that depth would be crushed instantly. Even the thickest submarine hulls must flex and groan under the stress. The slightest crack, the smallest imperfection, could mean disaster. Down here, the water isn't a gentle fluid. It's a force that can warp metal, shatter glass, and compress air into something almost solid. And yet, in this crushing darkness, life goes on. The first time scientists pulled up living creatures from the deep, they were baffled. How could delicate jellyfish, fragile crustaceans, and soft-bodied worms survive forces that would obliterate steel? It seemed impossible, until researchers began to understand the remarkable chemistry of life under pressure. Organisms that thrive in these extreme conditions are known as piezophiles, from the Greek piezo, meaning pressure-loving. To survive, every part of their biology, from cell membranes to enzymes, must be adapted to resist collapse. At the molecular level, pressure has strange effects. It squeezes molecules closer together, alters chemical bonds, and can even force water into proteins, causing them to lose their shape. For most living things, that would be fatal. Proteins are like the engines of the cell, and they only work when folded into precise three-dimensional shapes. But deep-sea organisms have evolved versions of these proteins that are flexible and stable under enormous pressure. Some use chemical stabilizers called piezolites, such as trimethylamine N-oxide, TMAO, which help prevent proteins from unfolding. In fact, TMAO concentration in fish increases with depth. The deeper you go, the more of it their bodies contain, up to a point. That's one reason deep-sea fish often have that distinctive fishy smell. TMAO breaks down into trimethylamine when exposed to air. So when you catch a whiff of seafood on land, you're smelling a molecule that, at some level, tells the story of survival under crushing pressure. Cell membranes, the delicate boundaries that hold life together, must also adapt. Under pressure, membranes tend to become rigid like glass. Deep-sea organisms modify their membrane fats, packing in more unsaturated lipids that stay flexible even when squeezed. It's as if they've engineered their own internal shock absorbers, keeping their cells supple in a world that's anything but. And then there's the body itself. Many deep-sea creatures are gelatinous, composed mostly of water, with few or no air-filled cavities. This makes them nearly incompressible. The secret is not to resist pressure, but to yield to it. A jellyfish at the surface would be crushed at 5,000 meters, 16,400 feet. But a jellyfish from 5,000 meters wouldn't even notice the pressure. It's built for it. There's a beautiful logic to this. The ocean doesn't tolerate rigidity. To survive here, you must be soft. One of the most extreme examples of adaptation is found in deep-sea crustaceans, the amphipods. These small, shrimp-like creatures live at depths of up to 10,000 meters, 33,000 feet. Some species, like Hirondelia gigas, inhabit the very bottom of the Mariana Trench. When researchers recovered specimens from those depths, they found something remarkable. Their exoskeletons contained aluminum hydroxide gel, likely extracted from seafloor sediments. This thin mineral coating may protect them from pressure and prevent calcium carbonate, which dissolves under high pressure, from eroding their shells. In other words, they build armor from the seafloor itself. Even more fascinating is how these amphipods manage buoyancy. Many deep-sea animals lack gas-filled organs, which would collapse. Instead, amphipods use lightweight, low-density oils and wax esters in their bodies to achieve neutral buoyancy. Their tissues are tuned like instruments, balanced perfectly against gravity and pressure. In the slightly shallower, but still formidable depths of 600 to 2,000 meters, 2,000 to 6,600 feet, lives another iconic creature, the giant isopod. Related to pillbugs, the tiny crustaceans that roll up when you touch them, these giants look like something straight out of a science fiction film. Measuring up to 50 centimeters, about 20 inches long, they creep slowly along the seafloor, scavenging for dead fish and whales. Their segmented shells are pale lavender or grey, and their enormous eyes, nearly the size of marbles, are adapted to catch even the faintest glimmers of bioluminescence. Giant isopods are patient survivors. Food is scarce in the deep, and they can go years without eating. In aquariums, some individuals have survived more than 5 years between meals. They simply slow their metabolism, waiting. Down here, everything is slow. The heartbeat of a deep-sea fish may beat just once every 10 seconds. Evolution has sculpted creatures that endure not through speed or strength, but through stillness. Pressure, paradoxically, has given rise to peace. But to truly appreciate the physics of this environment, it helps to compare it to something more familiar. At sea level, the air pressing on every square centimeter of your skin weighs about a kilogram, roughly 14.7 pounds per square inch. You don't notice it because the air inside your body pushes back equally. But if you were somehow transported to a depth of 1,000 meters, 3,300 feet, the water would add an extra 100 atmospheres of pressure, the equivalent of balancing a small car on your head. At 10,000 meters, it would be like trying to stand beneath the Eiffel Tower made of solid lead. For most materials, that kind of stress means collapse. Air pockets implode, solids compress, and even metals reach their limits. In 2014, Japanese engineers tested a titanium sphere rated for 11,000 meters, and found that even the smallest microscopic flaw could cause catastrophic failure. And yet, nature builds creatures that shrug it off. No thick armor, no industrial alloys, just organic chemistry. It's humbling to realize that while our technology strains to survive these depths, nature does it effortlessly. A deep-sea amphipod doesn't need a pressure hull, it is one. Scientists studying piezophiles often do so in high-pressure laboratories, stainless steel chambers where they can simulate the conditions of the deep. But keeping these organisms alive on the surface is notoriously difficult. When brought up too fast, they often rupture or disintegrate, like bubbles expanding in reverse. To study them, researchers use pressure-retaining traps, ensuring that specimens never experience a sudden change in environment. It's an elegant irony. To understand these fragile creatures, we must build machines as strong as submarines. One of the most intriguing discoveries about life under pressure is that it thrives on extremes. Experiments have shown that some bacteria isolated from the Mariana Trench can grow best at 1,000 atmospheres, not merely tolerate it, but prefer it. Remove the pressure, and they die. Their enzymes misfire, their membranes leak, their cells fall apart. What would kill us is, for them, home. The implications are profound. If life can adapt to the crushing depths of our oceans, why not to the icy oceans beneath the crusts of other worlds, like Europa, the moon of Jupiter, or Enceladus orbiting Saturn? Both are believed to harbor global oceans beneath kilometers of ice, with hydrothermal activity at their bases. Perhaps somewhere out there, in the dark seas of another world, creatures endure under pressures even greater than these, lit only by the faint glow of chemical energy. Back on Earth, pressure doesn't just shape biology, it sculpts behavior too. In the deep sea, movement is energy, and energy is precious. Many animals move slowly, conserving every calorie. Some are nearly motionless, drifting with the currents. Even predation here is often lazy, ambush rather than chase. The viperfish, for instance, lurks in the darkness with its mouth agape, using light organs to lure prey directly into its teeth. Energy efficiency is survival. The physics of pressure also dictates anatomy. Gas bladders, which shallow water fish use to control buoyancy, would implode at depth. So deep-sea species rely on oils, waxes, and even gelatinous tissues that compress little under pressure. Bones are thin, muscles sparse. Many fish here are translucent, their bodies ghosts of the medium they live in. When seen up close, they seem unreal, as if the ocean is dreaming them into being. The deeper you go, the more pressure defines everything. Even the chemistry of seawater changes. At 10,000 meters, water molecules are slightly more tightly packed, oxygen dissolves differently, and carbon dioxide reacts to form weak acids. These subtle shifts ripple through every aspect of biology, influencing metabolism, reproduction, and even evolution itself. Pressure isn't just a force, it's an entire environment. And yet, life doesn't just survive, it adapts beautifully. A 2021 study published in Nature Communications analyzed the genomes of deep-sea amphipods and found entire suites of genes devoted to repairing DNA damage and maintaining protein stability under pressure. Evolution has written resilience into their very code. It's a quiet triumph, one that happens molecule by molecule, century by century. The deep sea doesn't shout its miracles. It whispers them in enzymes and membranes, in creatures that glow softly against the dark. As we hover here in thought, suspended between physics and life, it's hard not to feel a certain humility. Our technology can visit the deep, but only briefly, only clumsily. Life has been here all along, enduring, adapting, perfecting itself in silence. And maybe there's a lesson in that, about flexibility, about patience, about the strength of being soft when the world presses hard. In the deep sea, survival isn't about resistance. It's about yielding, about letting pressure become part of you, rather than something to fight, because sometimes, to endure, you have to become the depth itself. As we drift deeper into the midnight zone, the last trace of sunlight is long gone. Above, the sea was blue, then dark, and now it is absolute black. But in this endless night, something extraordinary happens. The darkness begins to sparkle. Here, in the depths where no sunlight has ever reached, life creates its own illumination. Tiny flashes, pulses, spirals, and waves of living light shimmer through the water. A jellyfish ignites for a moment and vanishes. A shrimp flickers and disappears. An anglerfish dangles a glowing orb from its forehead like a living lantern. The deep sea, once thought to be a realm of total darkness, is in fact a realm of light, not from the sun, but from life itself. Scientists estimate that nearly 90% of deep-sea animals are bioluminescent, capable of producing light through chemical reactions within their bodies. From bacteria to jellyfish, from shrimp to sharks, this ability is everywhere. It isn't rare, it's the rule. Bioluminescence is one of nature's most elegant inventions, a universal language of the deep, shaped by evolution into art. But before we explore what that light means, it's worth understanding how it works. In essence, bioluminescence is chemistry turned to magic. It occurs when a molecule called luciferin reacts with oxygen, often catalyzed by an enzyme named luciferase. The reaction releases energy in the form of photons, light. Different species use different kinds of luciferin, colentrazine in many jellyfish and fish, bacterial luciferin in symbiotic microbes, and even unique compounds in fireflies on land. Despite their differences, the process is the same. Energy transformed directly into light with almost perfect efficiency. Biological light is far more efficient than any bulb humans have ever built. An incandescent bulb converts only about 10% of its energy into light. The rest becomes heat. Bioluminescence can reach nearly 100% efficiency. Pure light, no waste. The color depends on chemistry and environment. In the ocean, most bioluminescence appears blue or blue-green, with wavelengths around 470 to 490 nanometers, the range that travels farthest through seawater. Red and yellow light fade quickly with depth, so down here blue is the only color that matters. Yet some creatures break the rule. The dragonfish, for example, can emit and see red light, invisible to most prey. It uses this secret wavelength as a kind of night vision, hunting by a light no one else can detect. It's like having your own flashlight in a world of blindness. Light in the deep serves many masters. Every flicker, flash, or glow has a purpose. Survival written in luminescence. At first, it sounds paradoxical. How can light make you invisible? But in the deep, where the only light comes faintly from above, animals have evolved a trick called counter-illumination. By producing just the right amount of bioluminescent light on their bellies, they erase their own shadows. Predators looking up from below see only a faint glow matching the surface shimmer. To the eye, the animal disappears. The lanternfish, for instance, has rows of light-producing organs called photophores along its underside. It uses them like adaptive pixels, adjusting their brightness to match the ambient light above. It's the ocean's version of stealth technology, fine-tuned over millions of years. Other species, like certain squid, even use bacteria to achieve this camouflage. The Hawaiian bobtail squid hosts bioluminescent Vibrio fischeri in a special light organ. These bacteria live symbiotically inside the squid, fed and housed in exchange for their glow. At night, the squid controls the bacteria's light to blend perfectly with the moonlit water above, a living partnership between chemistry and biology. In a world of scarcity, light also becomes bait. Many creatures use it to attract prey straight into their jaws. The most iconic is the female anglerfish. Floating motionless in the black, she dangles a bioluminescent lure, a fleshy appendage called an eschar, from a rod-like extension on her head. The glow comes from symbiotic bacteria living within the lure. Curious prey, drawn to the light in the dark, swims closer, and then, suddenly, the jaws snap shut. The anglerfish's mouth is a cavern lined with translucent teeth, angled inward so nothing escapes. Her body, compressed and gelatinous, allows her to swallow prey as large as herself. Down here, meals are rare, and nothing goes to waste. Some squid use similar deception. The firefly squid, Wattersinia scintillans, produces synchronized waves of light along its body to confuse predators and lure plankton. Others eject glowing clouds, bioluminescent ink, to distract attackers while they flee. In the deep sea, light is not just beauty, it's strategy. It's also conversation. Many species use bioluminescence to communicate, to attract mates, coordinate movements, or warn rivals. Some fish flash in specific rhythms, unique to their species, like a Morse code of the ocean. In the flashlight fish, photophores beneath the eyes can open and close, creating precise blink patterns that help individuals keep together in schools. Others use light as a weapon of intimidation. The stoplight loosejaw, for instance, has red and green light organs. It can flash rapidly, startling smaller fish. The cookie-cutter shark glows along its belly, but keeps its throat dark, creating the illusion of a smaller fish from below. When predators approach, expecting easy prey, it attacks with circular jaws, carving a perfect round plug of flesh from its victim. It's brutal, ingenious, and strangely elegant. Light in the deep sea is communication at its purest, a dialogue of survival where sight has replaced sound and chemistry has replaced language. For a long time, humans had no way to witness this living light directly. The deep sea resists observation, it punishes intrusion. Early oceanographers dragged nets through the darkness, hauling up strange, broken creatures whose glow had already vanished. What we caught were only shadows of what truly lived there. That changed when a remarkable scientist, Edith Widder, found a gentler way to see. A marine biologist and ocean explorer, Widder devoted her life to studying bioluminescence and finding ways to observe it without scaring it away. In the 1980s, while working on a deep-sea mission, she suffered an electrical accident that left her temporarily paralyzed underwater, a terrifying experience that only deepened her fascination with the ocean's secrets. She realized that the bright lights and noisy thrusters of traditional submersibles terrified most deep-sea animals. So she designed a quiet, unobtrusive camera system called the Eye in the Sea. It used red light, invisible to most marine species, and sensitive detectors capable of recording faint glows without disturbance. In 2004, her device captured something the world had only imagined: a giant squid, alive, undisturbed, drifting through the black. Its arms coiled like ribbons. Its body pulsed faintly with light. For centuries, sailors had spoken of the Kraken, a legend of tentacles and terror. Now, science had finally met the myth. Widder's observations also uncovered something else: the idea of bioluminescent burglar alarms. Some small creatures, when attacked, release sudden bursts of light to attract larger predators. It's a desperate gamble. If I can't escape, maybe something bigger will eat you instead. Through her work, Widder showed that light in the deep is not decoration. It's survival. It's communication, strategy, defense, and seduction all at once. In a world where sound fades and smell is useless, light becomes the most expressive sense there is. When you think about it, bioluminescence is one of life's oldest languages. Long before humans discovered fire, long before the first eyes evolved on land, ancient bacteria were glowing in the sea. Some scientists believe the earliest bioluminescent life appeared more than 2 billion years ago, perhaps as a way to neutralize oxygen's toxicity. Evolution took that chemistry and turned it into poetry, signals, warnings, invitations, camouflage. Every flash you see in the deep is the echo of that ancient invention, a living continuation of the universe's oldest act, transforming energy into light. And that light continues to shape us, even on land. The glowing proteins first discovered in jellyfish, green fluorescent protein, or GFP, revolutionized modern biology. They allow scientists to visualize genes and neurons, to make the invisible visible. A gift from the deep now illuminates the inner workings of our own cells. If you could turn off the lights of your submersible and simply watch, the deep sea would look like the night sky. Tiny specks drift past like stars, constellations forming and dissolving in the currents. But unlike the heavens above, these stars are alive, pulsing, breathing, communicating. It's a galaxy that moves. There's a symmetry in that. The stars above burn with fusion, fire and violence. The stars below glow with chemistry, quiet and cold. One is the light of death, the other, the light of life. Both, in their own way, are eternal. Those who've seen it describe a feeling of almost sacred awe, the sense of floating in the cosmos, yet knowing you are inside the earth itself. Down here, light is fragile, fleeting, and precious. It appears only when it matters, to eat, to hide, to love, to live. And as we drift through this silent constellation, surrounded by sparks that pulse like heartbeats, we realize something profound. Even in the deepest dark, life refuses to disappear. It adapts, it communicates, it shines. Because to be alive, even in an abyss of silence and pressure, is to emit some kind of light. And so, in this ocean of darkness, everything glows. Under the weight of miles of ocean, the night grows absolute. Silence here is not just the absence of sound, it's a presence of its own, dense and complete. And yet, in this stillness, something moves. A faint pulse of light drifts by, then another. The darkness blinks. Down here, in the blackest waters on Earth, the hunters wait. They are not built like the predators we know from the surface. There are no sleek sharks or darting barracuda in the midnight zone. The deep sea demands a different kind of violence, one that relies on patience, deception, and grotesque ingenuity. When food is rare, evolution gets creative. These are the predators of the abyss, the anglerfish, the viperfish, the gulper eel, each a masterpiece of adaptation shaped by pressure, scarcity, and eternal night. Imagine floating motionless in total darkness, thousands of meters below the surface. There is no sun, no sound of waves, only the slow pulse of your own heart. You wait for something, anything, to cross your path. Days may pass, weeks. Down here, survival favors stillness, and so the hunters wait in silence, turning hunger into strategy. Few creatures capture the imagination like the anglerfish. With its gaping mouth, needle-thin teeth, and glowing lure, it looks less like a fish and more like a hallucination. Yet it's one of the most efficient predators on the planet. Female anglerfish, the only ones that hunt, live at depths between 1,000 and 3,000 meters, 3,300 to 9,800 feet. Their bodies are soft, flabby, and gelatinous, built not for speed, but for buoyancy. Muscles are unnecessary here. Energy is too precious to waste. Instead, the anglerfish has evolved one of nature's most chilling hunting tools, a bioluminescent lure. Sprouting from her forehead is a thin, flexible rod, the elysium, tipped with a glowing bulb called the esker. Inside that bulb live symbiotic bacteria that produce light through chemical reactions. She can wiggle this lure like a worm or make it pulse in rhythmic flashes. In a world without light, this faint glow becomes irresistible. Small fish, shrimp, and even other predators are drawn toward it. Curiosity fatally mistaken for safety. When they come close enough, her jaws open like a spring-loaded trap. Those jaws can unhinge completely, and her stomach can stretch to several times her own size. A meal that would drown or burst any other animal becomes fuel for weeks. Evolution, faced with scarcity, has decided better one enormous meal than 1,000 small ones. And then there's the anglerfish's private horror story, the males. In many deep-sea species, the males are tiny, sometimes 1/10 the female's size. They have no lure, no teeth worth mentioning, and almost no digestive system. Their purpose is singular, to find a female in the endless dark. When they do, they bite her. Enzymes dissolve their skin together until their bloodstreams merge. Over time, he loses his eyes, fins, and organs, becoming a living appendage, a parasite fused to her body. One anglerfish female may carry 6 males, permanently attached like grotesque ornaments. It sounds monstrous, but in a world where encounters are rare, it's evolution's pragmatic solution to loneliness. Down here, even love is an act of survival. If the anglerfish is the queen of deception, the viperfish is the knight of ambush, swift, silent, and terrible. Measuring about 30 to 60 centimeters long, roughly 1 to 2 feet, the viperfish is small compared to most ocean predators. But size doesn't matter when you're armed like this. Its teeth are so long they don't fit inside its mouth. Instead, they curve backward, forming a cage that impales anything unfortunate enough to wander too close. The lower jaw hinges open at almost a right angle, and the skull is jointed to swing forward, snapping shut with lethal precision. At depths of 2,000 to 3,000 meters, 6,600 to 9,800 feet, the viperfish waits motionless, suspended in the dark. Its spine has a built-in photophore, a tiny glowing lure that dangles in front of its face. When something moves toward it, the viperfish lunges, using a sudden burst of muscle energy stored in its body like a coiled spring. In the blink of an eye, the victim disappears into that nightmare grin. The viperfish's stomach is elastic and expandable, capable of holding prey larger than itself. Its body is semi-transparent, ghostly, with organs that shimmer faintly when struck by bioluminescent light. Some species even possess reflective scales that scatter light, breaking up their silhouette against the darkness like stealth camouflage. But perhaps the most extraordinary feature of the viperfish is its metabolism. In an environment near freezing, around 2 degrees Celsius, 35 degrees Fahrenheit, it moves in slow motion. It can wait days between strikes, conserving energy with the patience of a stone. The deep ocean rewards the still, not the swift. When viewed up close, the viperfish's skull looks almost like glass, delicate, translucent, and yet incredibly strong. Behind those teeth lies an evolutionary paradox, a predator built both for efficiency and for nightmare. Every detail serves a function. Every curve, every glow, every silence is a product of pressure and hunger. And then there is the gulper eel, perhaps the strangest hunter of all. It looks like something sketched in the fever dream of an artist who had never seen a fish before. Its mouth is enormous, a vast black sail that can engulf prey far larger than its own body. Its tail, long and whip-like, ends in a glowing pink light, which it waves gently like a baited line. At first glance, the gulper eel seems almost comical, a jaw attached to a wire, but the design is pure efficiency. The mouth acts as both trap and net, scooping up small fish, squid, and crustaceans that wander near. Unlike the anglerfish, which lures and waits, the gulper eel actively forages through the depths, swallowing whatever fits. Its scientific name, Uropharynx pelecanoides, means broad-throated pelican-like, a nod to its incredible gape. The skin is thin and nearly transparent, revealing organs faintly glowing beneath. Inside, the stomach expands like a balloon to hold vast amounts of food. Researchers have found specimens containing meals several times the eel's own weight, a grotesque but effective adaptation in a world where you never know when you'll eat again. The gulper eel can reach lengths of up to 1.8 meters, about 6 feet. Yet it weighs less than a house cat. Most of its mass is water, its flesh gelatinous and nearly boneless. There is no need for dense tissue when gravity means nothing and the ocean supports your weight entirely. Its tail light, a red or pink photophore, glows faintly in the dark, sometimes pulsing rhythmically. Scientists believe it may serve multiple purposes: to attract prey, to communicate with potential mates, or even to startle predators. When threatened, the eel can inflate its throat like a balloon, doubling its apparent size. Imagine a creature the length of your arm suddenly expanding into something that looks large enough to swallow you whole. It's enough to make even a predator hesitate. There's something almost tragic about the gulper eel's design. So perfectly evolved for an existence of scarcity, it seems both fragile and eternal, as if built more for surviving than living. In its luminous tail and impossible mouth, nature has condensed millions of years of trial and error into one improbable form. The deep sea is often described as quiet, but in evolutionary terms, it's anything but peaceful. Every adaptation is an answer to another. Every glow a response to a threat. It's an arms race played out in slow motion, where weapons and countermeasures evolve in tandem. For every predator that uses light to lure, there's prey that evolves to detect it. For every camouflage, there's a sharper eye. For every jaw that expands wider, there's a body that grows slipperier. Over time, these pressures sculpt forms that seem alien to us, creatures that blur the line between beauty and terror. Take transparency, for example. Many deep-sea animals are partially or entirely see-through. This isn't for aesthetic reasons, it's survival. In a place where light is scarce, being invisible is the best defense. The barreleye fish has a transparent dome on its head, allowing its eyes to rotate upward to spot prey silhouetted above. The glass squid hides its organs behind reflective tissue to avoid detection. Even some predators use transparency, a paradoxical cloak of invisibility that lets them approach without being seen until it's too late. The result is a constant tension between concealment and revelation, between those who glow to lure and those who vanish to live. Pressure adds another layer to this battle. At depths of 3,000 meters, 9,800 feet, the water is dense enough to slow sound, bend light, and crush air-filled cavities. Predators can't rely on hearing or speed. They hunt through patience, light, and touch. Some have lateral line systems, delicate sensors that detect minute vibrations in the water, allowing them to feel movement from meters away. In this darkness, the hunt is almost psychic, an exchange of cues invisible to us. The predator's lure glows faintly. The prey feels a current shift and hesitates. For a moment, there's balance. Then, in an instant, the silence breaks. A jaw unhinges. A light goes out, and the ocean swallows its sound once more. Predation here is brutal, but not wasteful. Every creature plays a role in recycling the scarce nutrients that drift down from above. Scientists call this the marine snow, a slow, steady rain of organic debris, dead plankton, fecal pellets, microscopic fragments of decaying life. Predators rely on this endless fall, directly or indirectly. They feed on the scavengers that eat the snow, or on the hunters that eat the scavengers. It's a food web built on patience and gravity, where every meal begins with death somewhere higher up. That's why deep-sea predators evolve for endurance, not abundance. The anglerfish may go weeks between hunts. The viperfish can fast for days, then devour half its body weight in one strike. The gulper eel may not eat for months. Metabolism's slow, heartbeat stretch. Down here, time itself seems to dilate. Evolution doesn't favor the biggest or the strongest here. It favors the patient, the adaptable, the grotesquely efficient. In the abyss, perfection looks strange. For centuries, these predators existed only in imagination. Sailors spoke of sea monsters that swallowed ships, of serpents with lantern eyes. But it wasn't until the age of submersibles and remote cameras that we truly saw them. And what we saw was far stranger than the myths. In 2005, researchers aboard the Monterey Bay Aquarium Research Institute's ROV Doc Ricketts filmed a gulper eel expanding its jaws to twice its body width, ballooning into an enormous black orb. In another dive, they captured viperfish ambushing prey with near-mechanical precision, their fangs snapping shut in less than a tenth of a second. Modern cameras reveal details that the naked eye could never see: transparent flesh rippling under pressure, tiny organs pulsing with chemical light, stomachs glowing faintly from bioluminescent prey digesting inside. It's as if every creature carries a galaxy within its body. And yet, for all our progress, we still know only fragments. Every expedition brings back new footage of creatures never before described, predators with impossible shapes and behaviors. Scientists estimate that up to 2/3 of deep-sea species remain undiscovered. The abyss keeps its secrets well. There's something hauntingly poetic about these hunters. Their lives, so alien, still echo familiar themes: hunger, solitude, adaptation. But in the deep, these ideas are stripped of comfort. A predator here doesn't hunt for sport or malice. It hunts because there is no other choice. Every flicker of light, every stretch of jaw, every swallowed meal is an act of pure necessity. The ocean doesn't reward cruelty or mercy. It rewards equilibrium. If you spend enough time thinking about these creatures, you begin to see them less as monsters and more as survivors of an impossible world, sculptures carved by physics and hunger. Each one embodies a truth that extends far beyond biology. That existence, even in darkness, finds a way to create form, purpose, and beauty. And so, in the crushing silence of the abyss, the hunters glow faintly in the dark, drifting through the void, with jaws half open. Their lights pulse slowly, their hearts beat sparingly. Every movement is deliberate, every breath is earned. If you could hover among them, silent, unseen, you'd witness a ballet of patience and hunger. A slow-motion dance where predator and prey are bound by the same laws, sculpted by the same hand. Evolution's patient, relentless artistry. The anglerfish waits with her glowing lure. The viperfish drifts, its fangs like needles in the dark. The gulper eel glides through the black, its luminous tail swaying like a falling star. They are the monsters of the deep, and yet, in their strangeness, they are perfect. Proof that even in the darkest corners of our planet, life still finds ways to astonish. Far below the reach of sunlight, where pressure is crushing and gravity feels irrelevant, the ocean begins to play by its own rules. Down here, in this twilight of evolution, life has taken on forms that seem to mock the imagination. Soft, translucent, fluid, and absurd. The creatures of the deep are nature's punchline to its own seriousness. It's as if the universe, after eons of precision and order, decided to loosen up and start improvising. If there's anywhere on Earth that feels like evolution's experimental lab, it's this one. Here, natural selection runs wild, unrestrained by sunlight, color, or the need to impress anyone watching. Shapes warp, eyes move to strange places, bodies melt into jelly or turn to glass. In a realm where everything must adapt to crushing pressure and eternal darkness, the result isn't chaos, but something close to surreal art. Among the most famous members of this strange menagerie is the blobfish, an animal so spectacularly misunderstood that it became the poster child for ugly, mostly because humans brought it somewhere it was never meant to be. The blobfish lives at depths between 600 and 1,200 meters, 2,000 to 3,900 feet, usually off the coasts of Australia and New Zealand. Down there, the pressure is up to 120 times that at the surface, enough to crush almost any air-filled structure. But the blobfish has no swim bladder, no bones to speak of, and very little muscle. Its flesh is a soft, gelatinous mass, slightly less dense than water, allowing it to float effortlessly above the seafloor like a slow-moving ghost. When it's in its natural environment, the blobfish looks fairly normal, a pale, soft-bodied fish, adapted to pressure that would flatten a human submarine. But when it's pulled up to the surface, that same pressure vanishes. Its body, no longer compressed, expands and collapses into a sagging, drooping form, the now famous melting face that won it the title of World's Ugliest Animal in a 2013 tongue-in-cheek poll. The irony, of course, is that it isn't ugly at all. It's perfectly engineered for its home, a fish made of jelly for a world made of weight. We only call it ugly because we see it out of context, like judging a diver fish for not surviving in air. Down there, it's as graceful as a balloon floating in slow motion. It has no need to fight or chase. It simply waits for edible detritus to drift its way. When food is rare, patience is elegance. The blobfish's strange design has inspired biologists and internet comedians alike, but what it truly represents is adaptation stripped of ego. There's no need for muscle or bone, where density itself is your enemy. Down here, softness isn't weakness, it's strategy. Nature's experimental lab, indeed. And apparently, it doesn't care much about public relations. If the blobfish is a symbol of surrender to the deep, the dumbo octopus is its whimsical cousin, a creature so improbably adorable that it looks like something from a children's dream, rather than an abyssal trench. Named for the rounded fins that protrude from its head like cartoonish ears, the dumbo octopus lives at depths of 3,000 to 5,000 meters, 9,800 to 16,400 feet, where pressure exceeds 500 atmospheres. That's like balancing a stack of elephants on every square inch of your skin. And yet, this delicate animal flutters through the blackness as if gravity were an opinion. It doesn't jet through the water like shallow octopuses. It doesn't dart or hide. Instead, it moves by gently flapping its ear-like fins, drifting more like a jellyfish than a hunter. Its arms are webbed with thin membranes that catch the water like silk, allowing it to glide with remarkable grace. Watching one move is hypnotic, a slow dance in liquid night. Unlike most of its relatives, the dumbo octopus doesn't ink. Ink would be useless here. It would simply hang in the water forever, obscuring nothing. Instead, its defense is invisibility through stillness. It can fold its fins, flatten its body, and become just another shape in the current. Its life is quiet, solitary, and slow. When scientists first observed one in a submersible near the mid-Atlantic ridge, it seemed almost curious, swimming up to the glass and hovering there as if examining us instead. Maybe it was. Evolution has given it large eyes, capable of capturing the faintest flicker of light from bioluminescent prey. It feeds mostly on small worms and crustaceans, swallowing them whole. There's no chase, no struggle, just the soft bloom of fins and the slow, inevitable embrace. Everything about the dumbo octopus feels like it was designed for a gentler world than ours. A creature made for stillness, surviving in silence. Scientists have found over a dozen species of dumbo octopus, some as small as a teacup, others nearly 60 centimeters, 2 feet, across. And while their forms vary, their attitude doesn't, serene, curious, and oddly endearing. Among the monsters of the deep, they are the dreamers, the gentle punctuation in an otherwise ruthless ecosystem. In the same depths where the dumbo octopus floats like a drifting thought, another marvel glides by, almost invisible until light hits it just right. The glass squid, also known as the cranchid, is exactly what its name suggests. A creature so transparent that you can see its organs through its body. At depths between 200 and 2,000 meters, 660 to 6,600 feet, the glass squid drifts in open water, suspended in an endless column of blue-black space. Its body is nearly cylindrical, its internal organs tucked neatly into a compact mass, visible through the clear, gelatinous flesh. It looks fragile, almost unfinished, as though evolution stopped midway through. But make no mistake, this is a highly specialized survival machine. Transparency is the ultimate camouflage. In a world without shadows, the best way to hide is to not be there at all. The glass squid's body lets most light pass through, scattering the rest so faintly that predators' eyes can't detect it. Even its eyes are partially transparent, with a single dark retina pointing upward to watch for prey or threats silhouetted against the faint glimmer of the surface. Some species have photophores that mimic the dim light above, counter-illumination, again, erasing their shadows. Others can expand or contract their pupils to match ambient brightness, an organic version of adaptive camouflage. Perhaps the most striking feature of the glass squid is its buoyancy system. Instead of a gas bladder, which would collapse under pressure, it uses a fluid-filled sac containing ammonium ions. The fluid is slightly less dense than seawater, allowing the squid to float effortlessly. It's a chemical defiance of gravity, science turned into serenity, and it's strangely poetic to think that an animal so fragile, so see-through, has persisted for tens of millions of years. Predators hunt it, currents toss it, yet the lineage endures. Transparency, it seems, can be its own kind of strength. But if the glass squid is invisibility perfected, the barreleye fish is something else entirely. Visibility redefined. Few creatures seem more like science fiction brought to life. Imagine a small, silvery fish, about 15 centimeters long, 6 inches, drifting upward in slow motion. Now imagine that its head, not just its eyes, but the entire top of its skull, is transparent, like a glass dome. Inside that dome, 2 large green orbs swivel freely, glowing faintly, staring upward through the ceiling of their own head. It sounds ridiculous, but that's exactly what it is. The barreleye's eyes are tubular, designed to capture the faintest light from above. They can rotate forward or upward, giving the fish a panoramic view of what's happening overhead. For decades, scientists believed its eyes were fixed, until high-resolution submersible footage in 2009 revealed the truth. The eyes move independently within their transparent casing, scanning the water like periscopes. The reason for this bizarre design is simple: hunting. The barreleye floats below colonies of siphonophores, long, jellyfish-like predators that trail tentacles lined with stinging cells. Other fish come to feed on these tentacles, and the barreleye steals them, darting in and out of danger. Its transparent shield protects its eyes from the stings above while it plucks bits of paralyzed prey. In evolutionary terms, it's the perfect compromise between curiosity and caution. Its head, glowing softly with refracted green light, might be one of the most beautiful sights in the ocean. But it's also eerie, a living window through which the brain can see. When you look at footage of it, you get an uncanny feeling that something is looking back at you with thought, calculation, even patience. Like many deep-sea fish, the barreleye barely moves. Its body is almost motionless, held steady by near-perfect buoyancy. Energy conservation is everything. Only when opportunity arises does it twitch into action, stealing food with surgical precision. Then it drifts again, still and watchful, a floating glass mind in a world without light. Taken together, these creatures form a gallery of oddities. The blobfish's jelly-like stillness, the dumbo octopus's serene grace, the glass squid's invisibility, the barreleye's living transparency. Each seems designed not by natural law, but by creative whim. And yet, every strange curve, every translucent layer, every improbable feature is a masterpiece of adaptation. The deep ocean removes the constraints of the familiar. There's no need for color when no one can see you. No need for speed when prey moves like ghosts. No need for bone when the water itself holds you up. Evolution, stripped of sunlight and competition, becomes an artist, experimenting, refining, occasionally joking. Some scientists refer to the deep as a slow-motion ecosystem. Energy moves sluggishly, generations unfold over centuries, and creatures evolve not for efficiency, but endurance. A fish that lives 2 miles beneath the surface doesn't have to be beautiful, it just has to persist. And yet, there's something undeniably beautiful about that persistence. When we look at these creatures, we tend to see oddities, things that don't fit our expectations of symmetry or grace. But that's only because they evolved in a world where our expectations don't apply. Down here, beauty isn't measured in form or color, but in function. Survival is the art, and everything else is improvisation. The dumbo octopus's gentle wings, the barreleye's crystal head, the glass squid's invisible body. They are proof that life doesn't need sunlight to create wonder. It only needs pressure, time, and imagination. If we could spend a lifetime observing the deep, we might find that what looks like madness is actually precision, evolution freed from aesthetic constraint. In the deep, evolution doesn't ask what works best, it asks what works at all. Sometimes the answer is elegant, sometimes it's absurd, sometimes it's both. And perhaps that's why the deep sea feels strangely human in its creativity. Messy, brilliant, improvisational. A reminder that nature, when left alone long enough, becomes its own artist. You can almost picture it. The ocean as a studio, gravity as the sculptor, and pressure as the critic, relentlessly testing every design. Some fail. Others endure for millions of years, unchanged. The blobfish drifts, unbothered. The dumbo octopus flaps its silent wings. The glass squid glows faintly as it vanishes into the black. The barreleye watches it all, eyes swiveling beneath its glass skull. And the ocean, that endless, weightless workshop, keeps creating over and over again. Nature's experimental lab indeed. Far below the light, in the black silence of the ocean floor, the earth itself breathes. It is not a gentle breath. It is hot, mineral, and full of creation. And it comes from places that, until recently, we didn't even know existed. For most of human history, we thought life on Earth was built upon sunlight, that every ecosystem, every creature, every breath somehow traced back to the energy of the sun. That belief seemed as fundamental as gravity itself. But in 1977, on a stretch of the Pacific seafloor near the Galapagos Islands, scientists found something that changed everything. They discovered life, thriving, complex, astonishing life, in a place where sunlight never reaches. It began with an expedition aboard a small U.S. research submersible called Alvin, operated by the Woods Hole Oceanographic Institution. The goal was to explore a region of the Galapagos Rift, a volcanic ridge running along the ocean floor about 2,500 meters deep, roughly 8,200 feet below the surface. The team expected to find little more than barren rock and sediment. After all, that's what the abyssal plain had always been: quiet, lifeless, cold. But as Alvin descended through the darkness and its lights swept over the seafloor, the crew saw something utterly unexpected. The cameras revealed towering chimneys of rock, venting clouds of black water that looked like smoke. The water shimmered, distorted by heat. And around these vents, in what should have been a dead zone, was a city of life. Giant white tube worms stood in dense clusters, each as tall as a human, their feathery red plumes waving in the current. Albino crabs scuttled across the rocks. Blind shrimp crowded in layers, their bodies glowing faintly in the sub's lights. It was a scene out of myth, as if someone had lit a fire at the bottom of the ocean and life had gathered to worship it. The scientists were speechless. One of them, Jack Corliss, later said, "It was like looking into another world." And that's exactly what it was. These strange structures, now known as hydrothermal vents, are born where the Earth's crust cracks open and seawater seeps down into the hot interior. There, the water meets magma-heated rock, reaching temperatures of over 400 degrees Celsius, 750 degrees Fahrenheit. It becomes infused with minerals, iron, sulfur, copper, zinc, and then, under immense pressure, it rises again through the cracks, bursting out into the cold ocean. When that superheated water meets the near-freezing seawater, usually around 2 degrees Celsius, 35 degrees Fahrenheit, the minerals precipitate, forming towering chimneys of metal and rock. These are the smokers. The black smokers vent iron sulfide and other dark minerals, producing plumes that resemble columns of black smoke rising from underwater factories. The white smokers, slightly cooler and richer in silica and barium, release lighter-colored plumes like pale steam against the dark. Together, they form an underwater skyline, a landscape built not by erosion, but by chemistry. What astonished scientists even more than the geology was the biology. Entire ecosystems were thriving here, without sunlight. Until that moment, all known food chains began with photosynthesis. Plants and algae captured energy from the sun and passed it upward through the web of life. But the creatures around these vents drew their energy from a different source entirely: the Earth itself. At the base of this strange new ecosystem were bacteria capable of chemosynthesis, a process where organisms derive energy from chemical reactions, not light. Instead of chlorophyll, these microbes used enzymes to harness the energy released when hydrogen sulfide, H2S, leaking from the vents, reacted with oxygen from seawater. The reaction produced sulfur and energy, which the bacteria used to build organic molecules, the foundation of all life. In essence, they were doing the same thing plants do, but without sunlight. For the first time, we had proof that life could thrive in total darkness, powered purely by geology and chemistry. The implications were enormous. The tube worms towering around the vents depended entirely on these bacteria. They had no mouths, no stomachs, and no digestive system. Instead, inside each worm's body was a specialized organ called a trophosome, packed with millions of chemosynthetic bacteria. The worms provided the bacteria with hydrogen sulfide from the vent water and oxygen from the surrounding seawater, delivered through their bright red plumes, which were red precisely because they contained hemoglobin adapted to bind both gases. In return, the bacteria produced nutrients for their host. It was a perfect partnership, a symbiosis so tight that the two forms of life were inseparable. Similar relationships appeared everywhere around the vents. Vent crabs scraped bacterial mats off the rocks to feed. Blind shrimp carried symbiotic bacteria on their shells. Clams and mussels hosted bacteria within their gills. The entire ecosystem, worms, crabs, shrimp, snails, fish, was built upon invisible chemical factories powered by volcanic heat. In this world, the energy of life didn't descend from the sun. It rose from the core of the Earth. The scientists who made the discovery struggled to contain their excitement. They had stumbled upon something that rewrote biology. The ocean floor was alive, not just with simple microbes, but with complex ecosystems independent of photosynthesis. Before that dive, few believed such a thing was possible. The azoic hypothesis, the idea that life could not exist below 600 meters, about 2,000 feet, had already been disproven in the 19th century, but no one imagined entire communities at 2,500 meters. It was like discovering a forest growing on the surface of Mars. And yet, the more they explored, the more they found. Hydrothermal vents turned up across the planet, along the East Pacific Rise, the Mid-Atlantic Ridge, the Indian Ocean. Each vent field was unique, like an island with its own endemic species, its own chemistry, its own rhythm of creation and destruction. Because vents are ephemeral, the chimneys collapse, clog, or shift as tectonic plates move. New ones open nearby. Whole ecosystems migrate across the seafloor, chasing the chemistry that sustains them. Imagine forests sprouting and dying every few decades, each reborn from volcanic fire. It's a violent, fleeting beauty. Life literally built on fire and metal. Among the most iconic inhabitants of these vent ecosystems are the giant tube worms, Riftia pachyptila. They can grow more than 2 meters, 6.5 feet, long, their white chitin tubes standing upright like a forest of pale reeds. The bright crimson plumes waving at their tops aren't flowers, they're gills, rich in hemoglobin. When Alvin's lights first illuminated them, the scientists were stunned by the color, so intense it seemed unreal against the monochrome of the abyss. These tube worms live without sunlight, without eyes, without mouths. They rely entirely on their bacterial tenants. The partnership is so complete that the worm's larvae start life free-swimming and mouthless, absorbing bacteria from the surrounding water as soon as they settle. Once the bacteria take hold, the worms stop growing digestive organs altogether. They no longer need them. Nearby, vent crabs, small pale creatures about the size of a human hand, scuttle among the chimneys. Their claws are often blackened by minerals. They feed on bacterial mats and carcasses of other vent animals. Some species live so close to the vents that their shells are etched by acid, constantly repaired by the creatures themselves. Then there are the blind shrimp, species like Rimicaris exoculata, that cluster in dense swarms directly on the vent openings. The heat there can reach over 380 degrees Celsius, 716 degrees Fahrenheit. But the water mixes with the cold seawater just enough for them to survive. Their shells shimmer with tiny symbiotic bacteria, which both feed them and serve as insulation from the heat. Their eyes have evolved into light sensors, tuned not for sunlight, but for the faint infrared glow of the vents themselves. They literally see heat. To witness these creatures alive is to feel like you're looking at the prototype of life itself, not refined or ornate, but pure function. No colors except what's chemically necessary, no ornament, just the collaboration of physics and biology made visible. Hydrothermal vents also challenged one of our oldest questions. Where did life begin? For centuries, scientists debated how life first arose from non-living matter. The classic idea was that it began in shallow sunlit pools, warm ponds struck by lightning or ultraviolet radiation, creating the first amino acids and simple molecules. But the discovery of vent ecosystems offered a radical new hypothesis. Perhaps life didn't begin in sunlight at all, but in darkness. Hydrothermal vents provide everything early life would need: heat, minerals, chemical gradients, and catalytic surfaces. The vent water contains hydrogen, carbon dioxide, sulfur, and metal ions, the same ingredients found in the organic molecules of cells. The surfaces of iron sulfide minerals can catalyze reactions that form amino acids and lipids. And the natural chimneys create compartments, tiny pores that could act like primitive cell membranes. In 1988, German chemist Günther Wächtershäuser proposed the iron-sulfur world hypothesis. that life began at hydrothermal vents, where catalytic reactions on mineral surfaces led to self-sustaining chemistry. Later, researchers like William Martin and Michael Russell expanded on this idea, showing how natural proton gradients at vents could power the formation of complex molecules, a natural version of the energy systems that still drive our cells today. Even the location of Earth's first life forms might have been similar to the vent fields we see today. Places like the Lost City hydrothermal field in the Atlantic Ocean, where towering white chimneys rise 60 meters, 200 feet high, venting warm, alkaline fluids rich in hydrogen. Unlike the acidic, high-temperature black smokers, Lost City vents are gentle, steady, and ancient, perhaps billions of years old. If life could start anywhere on this planet, such a place seems almost purpose-built for it. The discovery of vent ecosystems also transformed our search for life beyond Earth. If organisms can thrive in darkness, feeding on chemical energy alone, then similar ecosystems might exist on other worlds. Moons like Europa, around Jupiter, and Enceladus, around Saturn, are believed to harbor oceans beneath their icy crusts. Both show signs of hydrothermal activity, plumes of water vapor venting into space, rich in hydrogen and salts. If life exists there, it may resemble these vent communities, small, microbial, sustained not by sunlight, but by the inner heat of their planets. In that sense, every vent on Earth is not just a biological wonder, but a window into the cosmos. Some scientists even call them time machines. By studying vents, we glimpse both the past and the possible, the origins of life on Earth, and the potential for life elsewhere. It's humbling to think that long before plants turned sunlight into sugar, and long before animals breathed oxygen into motion, life might have begun around a volcanic vent in the dark, clinging to hot stone, drawing energy from the Earth's chemical breath. But even beyond philosophy, hydrothermal vents are crucial to our planet's ongoing balance. They recycle elements between the ocean and the crust, influencing global chemistry. The minerals they release feed plankton blooms thousands of kilometers away. Their ecosystems are resilient yet delicate, dependent on vent activity that can vanish overnight. When a vent field dies, so does everything around it. And now, another kind of threat approaches: us. Deep-sea mining companies have begun eyeing vent fields for their rich deposits of copper, cobalt, and rare earth metals. These are the same materials used in our electronics, our cars, our phones. It's easy to forget that while we once explored these places out of curiosity, we now look at them and see opportunity, or worse, profit. The irony is painful. The birthplace of life itself, scraped away for smartphone batteries. Scientists warn that the damage could be irreversible. Vent ecosystems recover slowly, if at all. Some vent fields may have persisted for thousands of years. One eruption, one machine, could erase them in hours. Maybe the most powerful thing the 1977 discovery gave us wasn't just scientific revolution, but perspective. It reminded us that life doesn't need us. It thrives in places we can barely survive. It grows in fire, in metal, in the impossible. And maybe that should inspire a little humility. Imagine floating in a submersible near one of these vents. The temperature outside your window might be near freezing, yet just a few meters away, a plume of superheated water boils upward, glowing faintly in the dark. The chimney beside you hums with minerals and life, worms swaying, shrimp clustering, crabs grazing like cattle in a meadow made of rock. You watch as the water shimmers with heat distortion. The lights from your sub catch motes of sulfur dust, swirling like fireflies. And you realize that you're looking at something older than sunlight, older than forests, older than breath. The ocean's first cities. Born of fire, sustained by stone, glowing softly in the dark. Far from the violent heat of hydrothermal vents, there exists another kind of deep-sea oasis, quieter, colder, but no less extraordinary. If vents are the fiery lungs of the Earth, then these are its slow, steady heartbeats. They are places where the planet leaks, not smoke or flame, but gas and salt and decay. Here, in the dark stillness of the ocean floor, life again finds a way to bloom from what seems like nothing at all. They are called cold seeps and whale falls, two very different phenomena united by one astonishing truth. Even in the deepest, most desolate parts of the ocean, death and chemistry can build worlds. Imagine the seafloor 2 kilometers down, a flat plain of silt and black mud, seemingly lifeless. The water is near freezing, about 2 degrees Celsius, 35 degrees Fahrenheit. There is no sunlight, no plants, no sound, but the whisper of distant currents. And yet, something moves. At first, it looks like smoke rising from the mud, faint, ghostly streams. But it's not smoke, it's methane. Methane seeps are places where hydrocarbons escape slowly from beneath the seafloor, bubbles of methane and hydrogen sulfide seeping upward from buried sediments and ancient fossil deposits. Unlike hydrothermal vents, these seeps are not hot. They're the opposite, cold, slow, ancient. The chemistry here is subtle, but powerful. As methane leaks into seawater, it reacts with oxygen and supports colonies of bacteria that can metabolize it, much like the chemosynthetic microbes at hydrothermal vents. These bacteria form dense microbial mats, thin white or orange films that coat the mud, rocks, and shells. To the human eye, it looks like mold growing on forgotten food, but each patch is a living factory, turning poison into life. These bacteria form the base of a unique food web. Mussels, clams, and tube worms cluster in dense colonies around the seeps, each harboring symbiotic bacteria in their tissues. They have evolved not to eat in the traditional sense, but to host life inside themselves. The mussels filter water rich in methane and oxygen. Their bacterial partners do the rest, producing nutrients. The worms absorb hydrogen sulfide through their skin and deliver it to the bacteria within their bodies. The result is a community built on gas, a city fueled not by sunlight, not by fire, but by slow chemistry. Cold seeps come in many forms. Some are gentle seeps where gases percolate softly through sediment, forming thin bacterial carpets. Others are more dramatic, with pools of dense, hypersaline water trapped in depressions, brine pools that shimmer eerily like liquid mirrors. These pools are so salty that they don't mix with the seawater above. They form distinct layers, with sharp boundaries you could literally see through. Submersibles hovering above them report that their robotic arms can dip into the pool, as though piercing another dimension. At the bottom of the Gulf of Mexico, for instance, there are brine lakes so dense that crabs fall in and never come out. Their bodies sink slowly into the saline abyss, preserved like relics. Around the edges of these pools, life crowds the borders, mussels, shrimp, worms, surviving right at the threshold between the possible and the lethal. Some brine pools glow faintly blue under the submersible lights, their surfaces rippling like oil. Scientists have nicknamed them with an almost biblical sense of awe. Latalant, the Orca Basin, Jupiter's lake. They are the strangest seas within the sea, places where water sits on water, where chemistry replaces sunlight, and where ecosystems thrive on the margins of what life can endure. The creatures of the cold seeps are no less specialized than those of hydrothermal vents, but their lives move on a slower clock. A hydrothermal vent may last a few decades before collapsing, but cold seeps can persist for centuries or even millennia. The methane flow can be steady for ages, providing a constant, if faint, source of energy. The animals that live here have evolved to match that pace. Tube worms at cold seeps, for example, grow incredibly slowly. Some species, such as Lamellibrachia luimesi, have lifespans estimated at over 250 years, making them among the longest living animals on Earth. They anchor themselves deep into the sediment, tapping into pockets of sulfide, while their symbiotic bacteria produce nutrients inside them. They are the redwood forests of the deep, ancient, silent, enduring. Above them drift colonies of mussels, their shells layered in bacterial film. Crabs scavenge among them, picking at the mats like gardeners. Sea cucumbers and brittle stars creep across the mud. To an untrained eye, it may look barren. But through the lens of a submersible camera, the seafloor glows with motion, a slow choreography of chemical life. What connects these cold seeps to the rest of the ocean is an invisible current, death. The organic matter that falls from the surface, the so-called marine snow of tiny corpses and debris, feeds the microbes that sustain the seeps. Every plankton bloom, every whale migration, every storm above eventually contributes to this slow rain of nutrients below. And sometimes death itself arrives whole. A whale fall is one of the most haunting and beautiful events in the deep sea. When a whale dies at the surface and its body sinks, it becomes a world unto itself. A single carcass, weighing tens of tons, can take months to drift down through the water column, falling in silence through darkness until it hits the seabed, an event that can feed life for a century. At first, scavengers arrive. Sharks, hagfish, sleeper sharks, and giant isopods tear into the soft flesh, stripping it down within weeks. Crabs and amphipods swarm the bones. Then, as the feast continues, smaller creatures move in. Worms, snails, bacteria, beginning the long process of decomposition. Scientists divide the whale fall's transformation into three main stages. The first is the mobile scavenger stage, where large predators devour the soft tissue. The second is the enrichment opportunist stage, where smaller organisms colonize the bones and surrounding sediment, feeding on the oily remains. The final phase, the sulfophilic stage, can last for decades. Here, bacteria that digest fat within the bones release hydrogen sulfide, creating a mini ecosystem similar to a hydrothermal vent. The bones themselves become chemical engines. Around them gather mats of chemosynthetic bacteria, along with clams, mussels, and worms that feed on the sulfur compounds. Entire new communities grow from the decay of one enormous creature. It is, in every sense, the circle of life, just slower, colder, and deeper. Among the strangest inhabitants of whale falls are the so-called zombie worms, Osedax. They are small, fragile, and eerily beautiful, like crimson threads swaying in the water. They have no mouths, no stomachs, no digestive tracts. Instead, they bore into whale bones using acid secreted from their roots, and within those roots live symbiotic bacteria that digest fat and protein from the bone itself. The worms then absorb the nutrients their bacterial partners produce. Discovered in 2002 off the coast of California, Osedax changed our understanding of how the deep ocean recycles its dead. Their bodies are sexually dimorphic in a way almost as strange as the anglerfish. Females can be several centimeters long, while the males are microscopic, hundreds of them living inside the female's tube, serving as permanent mates. In the abyss, even reproduction becomes a form of partnership against isolation. Whale falls provide food not just for the worms, but for entire chains of life that follow. Crustaceans graze on the bacterial mats. Snails feed on the worms. Fish and octopuses linger nearby, drawn by the scent of decay. Each whale that dies becomes, for a time, an island, a self-contained universe of energy in a desert of cold. A single skeleton can support thousands of species. Some have been found still sustaining bacterial communities 75 years after the whale's death. That's longer than many forests last on land. What's remarkable is how similar these whale fall ecosystems are to the communities around cold seeps and vents. All three depend on chemosynthesis, life built not on light, but on chemical reactions. Whether it's methane bubbling from the mud, sulfur spewing from vents, or the oils of decaying bone, the principle is the same. Energy can come from the earth, not the sky. It suggests something profound. Life doesn't need to begin in sunlight at all. Anywhere there is a steady flow of energy, chemical, thermal, or otherwise, life finds a foothold. It's no wonder that astrobiologists often cite cold seeps and whale falls when imagining extraterrestrial ecosystems. On an icy moon like Enceladus, where tidal forces keep an ocean warm beneath the ice, life might look very much like this: small, patient, feeding not on fire or light, but on chemistry and decay. In that way, every whale that falls to the seafloor becomes a kind of parable: from death, life; from silence, community; from the collapse of one body, the birth of countless others. The deep ocean doesn't waste anything. Even tragedy becomes creation. Cold seeps turn geological leaks into oases. Whale falls turn death into decades of nourishment. The same chemical processes that power these ecosystems may be echoes of the very first reactions that sparked life itself billions of years ago. It's easy to imagine the scene: a dark plain, 2,000 meters down. In one corner, a seep bubbles quietly, surrounded by white worms and mussels. Not far away, the ribcage of a whale lies half buried in the silt, its bones carpeted in red Osedax worms and bacterial mats that shimmer faintly like frost. Crabs crawl between the bones. Shrimp drift past. Everything is still, but everything is alive. The currents whisper over it all, slow, ancient, eternal. And if you could hover there long enough, you'd see time itself made visible. The patient recycling of energy, the endless cycle of creation and return. A methane bubble rises and bursts. A worm sways in the current. A whale's bones dissolve into mineral dust. And from it all, life begins again. In the darkness of the deep ocean, where sunlight dies and pressure rules, legends have always had room to grow. For centuries, sailors whispered of monsters that lived beneath their ships, creatures with arms long enough to drag a vessel into the depths, eyes like lanterns, and beaks that could slice through oak. They gave these beings names: the Kraken, the Sea Devil, the Leviathan. Most dismissed those stories as seafarers' fantasy, born from fear, exhaustion, or rum. But the truth, as it often does in the deep, turned out to be stranger than fiction. Because those legends were not entirely wrong. There really are giants in the abyss, enormous alien creatures with eyes the size of dinner plates and arms that can wrap around a bus. They are the giant squid, and its even more formidable cousin, the colossal squid, two of the most elusive and awe-inspiring animals on Earth. For centuries, no one had ever seen one alive. All that reached us were fragments, tentacles washed ashore, strange scars on sperm whales, beaks found in stomachs. These were the fossils of the present, clues that something unimaginably large drifted below. In 1857, a Danish naturalist named Japetus Steenstrup examined pieces of a massive tentacle found off Iceland and realized it belonged to a previously unknown species. He named it Architeuthis dux, the ruling squid. Word spread quickly through Europe's newspapers, and the Kraken of myth suddenly had a Latin name. Still, for more than a century afterward, it remained unseen in life. Sailors found carcasses floating in the Atlantic, some over 13 meters, 43 feet, long. But they were always dead, pale, and half-eaten, their soft bodies collapsing under their own weight once the ocean's pressure was gone. No one knew what they really looked like, how they moved, or even if they hunted at all. Then came a revelation. There wasn't just one giant squid. There was another, bigger, stranger, and tougher. The colossal squid, Mesonychoteuthis hamiltoni, was first identified in 1925 when whalers found enormous tentacles inside the stomach of a sperm whale. But it wasn't until 2007 that a full specimen was recovered, caught accidentally by a New Zealand fishing vessel in the cold waters of the Antarctic. It measured about 10 meters, 33 feet long, and weighed almost half a metric ton, 1,100 pounds. At first glance, it looked similar to its Atlantic cousin, but closer inspection revealed astonishing differences. The colossal squid's tentacles weren't lined with simple suckers like the giant squids. Instead, they bore rotating hooks, serrated, swiveling weapons that could latch and tear. Its body was thicker, heavier, built for strength rather than speed. Its arms were muscular, its flesh dense with ammonia-rich fluid to maintain buoyancy in freezing water. And its eyes, each nearly 30 centimeters across, about 12 inches, were the largest ever known in the animal kingdom. Not metaphorically, literally the biggest eyes on Earth. Those eyes are not just impressive, they are vital. In the pitch black of the deep, sight is everything. The colossal squid's enormous pupils can capture even the faintest glimmer, the glow of a bioluminescent creature disturbed by movement, or the pale outline of a predator's silhouette. Each eye is like a biological telescope, tuned to detect shadows against darkness. And those shadows often belong to the only creature large enough to hunt them, the sperm whale. The relationship between squid and sperm whale is one of the ocean's most titanic rivalries, a predator-prey dynamic that could have inspired centuries of myth. Sperm whales dive as deep as 1,000 to 2,000 meters, 3,300 to 6,600 feet, staying submerged for over an hour as they search for squid. Their sonar clicks echo through the dark, like the pulse of an unseen hunter. When a whale finds a squid, the encounter is not gentle. Deep scars on sperm whale skin tell the story. Circular marks from suction cups and slashing wounds from hooks. Some of these scars measure half a meter across, almost 2 feet. The whale's jaws can crush, but the squid's arms fight back with coiled power, wrapping and tearing. It's a battle fought in total darkness, unseen by human eyes, yet etched into the flesh of both combatants. No one wins easily. Even for the whale, one of the largest animals ever to live, a fully grown squid is a worthy adversary. The giant squid may stretch 13 meters long, the colossal shorter but heavier, each one armed with 8 arms, 2 tentacles, and a beak capable of slicing through bone. When you imagine that struggle, a whale the length of a city bus twisting through the abyss, locked with a creature of pure muscle and hooks, you start to understand why sailors spoke of monsters. They weren't inventing terror, they were remembering echoes. And yet, for all its fame, for all the legends it inspired, no one saw a live giant squid in its natural habitat until the 21st century. For over 100 years, scientists tried everything: deep-sea trawls, baited hooks, even using sperm whale recordings to lure one in. They found bits and pieces, never the living whole. The animal seemed determined to remain myth. Then, in 2012, that myth finally broke. A team led by Japanese researchers Tsunemi Kubodera and Edith Widder, yes, the same deep-sea explorer who revolutionized bioluminescence research, used a specially designed camera system to film deep-sea creatures without startling them. They descended off the Ogasawara Islands south of Japan, deploying a faintly glowing lure mimicking the bioluminescent light of a jellyfish in distress. Hours passed. Then, out of the black, a shape emerged. First, a flash of silver. Then, a long, coiling arm, gleaming gold in the submersible's light. And finally, the unmistakable silhouette of a giant squid, its eyes reflecting like moons. It hovered for a moment, inspecting the lure, its tentacles curling in slow motion. The scientists watched in stunned silence. After centuries of myth, there it was, real, living, magnificent. The creature was about 3 meters, 10 feet long, though the team estimated it would have reached over 8 meters, 26 feet, with its full tentacles extended. Its skin shimmered with a metallic sheen, flashing from gold to silver as it turned. For the first time, we could see how it moved, not thrashing or monstrous, but deliberate and graceful, gliding with slow, rhythmic strokes. When the footage was released, it was like watching a myth exhale. The Kraken was real, just quieter, softer, and more beautiful than we'd imagined. The giant squid itself is a remarkable creature, perfectly adapted for life in the open ocean's twilight zone. Its arms are lined with hundreds of suction cups, each rimmed with tiny teeth that help it grip struggling prey. Its beak, hard as bone, can shear through fish and crustaceans, and its feeding tentacles, longer than its body, can shoot out like harpoons to snare prey before reeling it back in. Its anatomy tells a story of precision, not aggression. Its body is streamlined for vertical movement, rising at night to hunt and sinking by day into darkness. The giant squid's flesh is buoyed by ammonia-filled fluids that reduce density, making it neutrally buoyant, an elegant balance that lets it drift effortlessly, conserving energy in the cold depths. But despite its monstrous reputation, the giant squid is a shy creature. It has no natural armor, no thick shell or hard bone. Its defense is escape, and its enormous eyes. Those eyes, up to 27 centimeters, 11 inches across, are more than vanity. They are survival tools. In the deep, light behaves differently. When a large object, like a whale, moves through the water, it disturbs bioluminescent plankton, creating faint trails of light. A squid with eyes that large can detect those disturbances from over 100 meters, 330 feet, away, a warning of a predator approaching long before it's visible. To the squid, the ocean is not empty. It's alive with invisible flashes, like stars behind fog. And in that silent constellation, survival depends on seeing before being seen. The colossal squid, though similar, lives deeper, mostly in the cold, dark waters of Antarctica, often between 1,000 and 2,200 meters, 3,300 to 7,200 feet. Its lifestyle is slower, more methodical. Its body mass is greater, its metabolism lower. It doesn't chase so much as wait, a patient ambusher drifting near the bottom, letting prey come to it. Unlike the giant squid's long whip-like tentacles, the colossal squids are shorter but heavily muscled. Each sucker has 3 sharp claws that can rotate 360 degrees. Imagine being caught in that. It's less like being grabbed by suction and more like being snagged by hundreds of meat hooks. The two species may never meet. Their ranges barely overlap. But together, they define the upper limits of what a soft-bodied animal can become. Without bones, armor, or lungs, they reach lengths longer than most dinosaurs, powered only by muscle, chemistry, and patience. And yet, despite their size, they remain almost invisible. Giant squids have been found washed ashore in New Zealand, Spain, Newfoundland, and Japan, often in pieces, their arms tangled in fishing nets. The colossal squid, rarer still, has been seen only a handful of times. Each specimen deepens the mystery rather than solving it. We have dissected their eyes, measured their hooks, analyzed their beaks, but we still know almost nothing of how they live, how they mate, where they spawn, how they die. They are the ocean's quietest giants, slipping through the darkness like living phantoms. The myths, however, never really left. In a way, they only evolved. The Kraken of Norse legend, said to be so vast it could wrap its arms around a ship, likely came from encounters with giant squid remains. In 13th century Icelandic sagas, sailors spoke of monstrous Hafgufa, a sea creature whose rising bulk was mistaken for land. In the 1750s, a Danish bishop named Erik Pontoppidan described it as round, flat, and full of arms, a perfect description if one had only glimpsed the thrashing tentacles of a dying squid. Those myths persisted because they were, in essence, eyewitness accounts of truth, distorted by fear but anchored in reality. The ocean hid its giants, but every now and then it offered a clue: a tentacle in a whale's mouth, a corpse on a beach, a shadow in the water. Even today, the image of the Kraken endures, not as a monster, but as a symbol of the unknown. It reminds us that the ocean is still vast enough to keep secrets, still deep enough to humble us. When you look into the eye of a giant squid, whether through footage or preserved specimen, there's an uncanny feeling of recognition. That enormous, unblinking eye, dark and intelligent, seems to hold centuries of silence. It's not the look of a monster, it's the look of something that has seen too much. Lightning storms from below, whale song through water, the slow drift of continents. The deep sea's giants are not beasts of horror. They are engineers of survival, fragile yet immense, soft yet formidable. Reminders that power doesn't always roar. Sometimes it simply drifts. And somewhere down there, as you read this, one might be gliding silently through the black, its golden skin shimmering faintly in the cold. Its eye, that enormous, perfect window, watching, waiting, reflecting the glow of creatures that pass like stars. A real Kraken. Not imagined, not myth. Just another miracle we almost didn't believe in. For all its beauty and mystery, the deep sea has always kept its distance from us. It lies beyond sunlight, beyond reach, and for most of history, beyond imagination. Humans are fragile creatures built for air and light, yet somehow we've always been drawn to the dark. The story of our exploration of the deep ocean is, in many ways, the story of our defiance. A gradual descent, not of falling, but of reaching. From the first weighted ropes dropped by sailors to the sleek submersibles of today, each generation has tried to go deeper, to see further, to bring a little light into the black. It began humbly. For centuries, we could only guess what lay beneath. Aristotle believed life couldn't exist past a few hundred meters. Even as late as the 19th century, the idea of a lifeless deep ocean, the Azoic hypothesis, persisted. Then came the HMS Challenger expedition, 1872 to 1876, which changed everything. It hauled up hundreds of new species from depths once thought barren. But what those explorers could not do was see the world they had discovered. That would have to wait for a new kind of vessel, one that could survive where sunlight and sound fade away. In 1964, a small American submersible named Alvin made its first dive. Just 7 meters long, 23 feet, it looked more like a bathyscaphe crossed with a soap bubble than a spaceship. But that little craft would become one of the most important tools in the history of ocean science. Operated by the Woods Hole Oceanographic Institution, Alvin could carry 3 people down to depths of over 4,000 meters, 13,000 feet. Its titanium sphere was barely large enough for its crew to sit shoulder to shoulder, surrounded by lights, cameras, and small viewports like portholes to another world. In its early years, Alvin made hundreds of dives, locating lost hydrogen bombs, exploring seamounts, mapping trenches. But its defining moment came in 1977, when it descended to the Galapagos Rift and discovered the first hydrothermal vents, towering chimneys spewing mineral-rich water, surrounded by life no one had ever seen before. That single dive redefined biology and transformed our understanding of life on Earth. From that moment, the abyss was no longer empty, it was alive. Alvin went on to make thousands of dives, exploring the Titanic wreck in 1986, mapping deep ecosystems, and becoming a kind of ambassador for human curiosity. Over decades, it has been rebuilt and upgraded multiple times. Its most recent version can reach nearly 6,500 meters, 21,300 feet, capable of exploring 98% of the ocean floor. Not bad for a vessel smaller than a van. If Alvin was the quiet pioneer, then James Cameron's deep-sea Challenger was the dramatic breakthrough of modern times. In 2012, the filmmaker and explorer, known for directing Titanic and Avatar, piloted a one-man submersible of his own design to the deepest known point on Earth. The Mariana Trench, 10,908 meters, 35,787 feet below the surface. The vehicle itself was a marvel of engineering. Unlike traditional spherical submersibles, it was long and vertical, a lime green torpedo over 7 meters tall, 23 feet, with Cameron sitting inside a pressure sphere barely wide enough to move his arms. The outer hull was designed to withstand over 1,000 atmospheres of pressure, enough to crush steel. Inside, Cameron was surrounded by LED screens, joysticks, and recording equipment. Outside, robotic arms, lasers, and 3D cameras were mounted to capture the alien world below. The descent took 2.5 hours. For that entire time, the radio went silent. Communication at those depths is nearly impossible. When he finally reached the bottom, Cameron looked out through a small viewport into a world no human had ever seen firsthand. The seafloor stretched flat and grey, covered in fine sediment, dotted with strange organisms, translucent shrimp, ribbon-like worms. He spent nearly 3 hours exploring, gathering samples and filming the desolate landscape. Later, he described it as a completely alien world, peaceful, desolate, and strangely beautiful. The footage, used in his documentary Deep Sea Challenge 3D, wasn't just cinematic, it was scientific. The dive yielded new species and geological samples, and proved that human exploration of the deepest ocean was still possible, even in an era dominated by machines. But as submersibles became rarer and more expensive, a new era of deep-sea exploration began, one defined not by people inside the ocean, but by machines sent into it. Enter the ROV, the remotely operated vehicle. ROVs are robotic submarines tethered to a ship by long fiber-optic cables. They carry high-definition cameras, robotic arms, lights, and sensors, all controlled by pilots from the surface. Without the need for life support, ROVs can dive deeper, stay longer, and take greater risks than any human ever could. Institutions like the Schmidt Ocean Institute, the Monterey Bay Aquarium Research Institute, MBARI, and Ocean X have made ROVs the backbone of 21st century ocean exploration. Ocean X, for instance, operates the Ocean Explorer, a 285-foot, 87-meter research vessel that looks like something between a science lab and a spaceship. It carries state-of-the-art ROVs and manned submersibles, laboratories, sonar systems, and broadcast studios, allowing discoveries to be shared with the world in real time. The ship's team has filmed deep-sea sharks, giant squid, coral forests, and ancient shipwrecks, often streaming the footage live online. Their motto: explore, discover, share. Meanwhile, the Schmidt Ocean Institute's vessel Falkor 2 uses advanced ROVs like Sebastian, capable of diving to 4,500 meters, 14,700 feet. In recent years, Sebastian has captured breathtaking footage of deep coral reefs, glass sponges, and previously unknown species, including, in 2020, a massive siphonophore nearly 45 meters, 147 feet long, possibly the longest animal ever recorded. These robotic explorers are tireless. They can hover in place for hours, collect samples with precision, and map sea floors in exquisite detail. Every dive expands the known boundaries of our planet, often by mere pixels, but always forward. And unlike human divers, they don't get seasick. In many ways, the deep sea is becoming one of the last frontiers of human mapping, the final geography. Despite all our satellites and charts, we still know more about the surface of Mars than the bottom of our own oceans. As of the 2020s, less than 25% of the seafloor has been mapped in high resolution. The rest, some 360 million square kilometers, remains uncharted. That's where the Seabed 2030 project comes in. Launched in 2017 by the Nippon Foundation and GEB Co., the General Bathymetric Chart of the Oceans, Seabed 2030 has a bold goal: to map the entire ocean floor by the year 2030. Every ridge, trench, and plain, every contour of the Earth beneath the waves. To do this, scientists are gathering sonar data from research ships, fishing vessels, private yachts, and even autonomous underwater drones. Each year, new data adds thousands of square kilometers to the map, gradually revealing the true shape of our planet. Why does it matter? Because mapping isn't just curiosity. It's crucial for understanding earthquakes, tsunamis, climate change, and ecosystems. The ocean floor stores the history of our planet in layers of sediment, volcanoes, and fault lines. To understand Earth, we have to see all of it. As project director Jamie McMichael Phillips put it, "You can't manage what you haven't mapped." The initiative is ambitious, but it's working. By 2024, over 20% of the ocean had been mapped, double the coverage since the project's start. With every year, the outlines sharpen. The seafloor's invisible mountains and valleys become real, and the dark unknown grows smaller. It's poetic, in a way. While we send telescopes to study galaxies billions of light years away, we're still filling in the blanks of the world beneath our feet. The tools have changed, from Alvin's steel sphere to fleets of autonomous robots, but the desire behind them remains the same. It's the same curiosity that drove sailors to imagine the Kraken, that sent James Cameron to the trench, that keeps researchers peering into glowing screens aboard rolling ships at 3 a.m., watching a robot's camera feed flicker with the shimmer of an unknown creature. Even now, with our technology, the deep resists full understanding. It's too vast, too changeable, too alien. But the glimpses we've gained, the vents, the giants, the ghostly worms, have already changed how we see life itself. And perhaps that's the most remarkable thing about human encounters with the abyss. Every time we go down there, every time we send light into that darkness, what we find isn't just new species or strange landscapes. We find perspective, because the ocean reminds us, gently but firmly, of how little we truly know. That beneath the surface of our own planet lies a world that could swallow us whole, and still, somehow, chooses not to. And as our machines hum quietly in the depths, mapping, filming, sampling, the abyss reflects their light back, as if to say, "I've been here all along. Welcome to my world." The deeper we go, the less it feels like exploration, and the more it feels like introspection. The ocean, in all its silence and pressure, becomes a mirror, not one of glass or reflection, but of meaning. The abyss, for all its distance from us, speaks of something within us, the part of the mind that remains dark, unlit, unknown. It's no wonder that philosophers and psychologists have long used the ocean as metaphor. Sigmund Freud once compared the unconscious mind to the sea, vast, powerful, and hidden beneath a thin surface of awareness. Carl Jung went even further, calling it the collective unconscious, the shared deep of human experience, filled with archetypes and symbols that surface only in dreams. To descend into the abyss, then, is not unlike diving into one's own psyche. The upper ocean, bright and shallow, is consciousness, busy, visible, full of movement. But beneath lies layer after layer of darkness, memory, fear, instinct, longing, each one denser than the last. What we call the midnight zone of the ocean could just as easily describe the mind, a place where light fades, where familiar shapes blur, where the strange begins to make sense. Perhaps that's why the deep sea feels so profoundly human. When we stare into that blackness, we are looking into ourselves, into the parts of us we rarely confront. The abyss isn't empty, it's just unexplored. In our time, it's easy to forget that the ocean and the cosmos are two sides of the same mystery. Both are vast, silent, and mostly unknown. Both have lured explorers with the same hunger, the need to know what's out there or down there, even if we don't yet understand why. Space, with its glittering stars and cold emptiness, became the stage for human ambition, the great outward journey. The ocean, meanwhile, became the inward one, the descent rather than the escape. Yet in terms of difficulty, danger, and wonder, they are equals. In the vacuum of space, the pressure is nothing. In the deep sea, it is everything. A spacecraft in orbit faces 0 atmospheres. A submersible in the Mariana Trench faces over 1,000. Space is emptiness made infinite. The ocean is weight made eternal. Both crush the body, but in different directions, one outward, one inward. It's fascinating how we've always romanticized one and feared the other. We send billionaires and telescopes into orbit with awe and applause. Yet only a handful of humans have visited the deepest trenches of their own planet. We look up and dream. We look down and hesitate. Maybe that says something about us, that we prefer the clean, starry unknown to the wet, suffocating one. The ocean is too close, too reflective. You can't see your own reflection in the stars, but you can feel it in the sea. Still, the ocean remains the most alien world we've ever visited. If we stripped away the mythology and looked purely at its physics, its crushing pressure, its absence of light, its strange forms of life, we'd have to admit, it's not that different from another planet. In fact, when scientists imagine what life might look like on distant worlds, they look to the deep sea first. Moons like Europa and Enceladus, orbiting Jupiter and Saturn, are encased in thick shells of ice, beneath which lie entire oceans. Space probes have detected plumes of water vapor venting into space from their surfaces, filled with salts, minerals, and organic molecules. In other words, alien hydrothermal vents. If life exists there, it may look remarkably familiar. Microbial mats feeding on chemical gradients, tube worms or shrimp-like organisms surviving on heat and minerals instead of sunlight. The same processes that power our deepest ecosystems could be universal, repeating themselves wherever chemistry and time align. In that sense, every dive into Earth's abyss is also an act of cosmic exploration. The submersible becomes a spaceship, the pilot an astronaut of the inner universe, the hydrothermal vent a portal not to hell, but to possibility. Astrobiologists often say, to find life elsewhere, first understand it here. And perhaps that's what the ocean has been trying to tell us all along, that the key to understanding the universe isn't found in the stars, but in the quiet, unseen places beneath our own feet. The abyss is not just a physical space, it's a metaphor for fear, for curiosity, for everything we cannot yet explain. We project our anxieties onto it, monsters, ghosts, Kraken, Leviathan, but also our hopes. It holds our collective imagination in suspension, an eternal what if. We fear it because it resists control. We are drawn to it because it resists understanding. It's both the limit and the invitation, the line between what we know and what we're willing to risk to know more. Every expedition into the deep, from Alvin to ROVS to James Cameron's solitary descent, is a small act of defiance against the unknown, a way of saying, we are afraid, but we'll go anyway. And that courage, repeated in silence at the bottom of the world, becomes a mirror for something essential in us. The same spark that once made our ancestors cross deserts, build fires, and look up at the night sky. The ocean is our reminder that curiosity and fear are not opposites. They are twins, born of the same longing to understand. One warns us of danger, the other pushes us through it. Without both, exploration would not exist. When you look at the ocean from above, its surface gleaming under the sun, it's hard to believe that beneath that calm lies a realm so vast and alien. And yet, that's exactly what makes it beautiful. It's a world within our world, infinite in its own way, a silent landscape that humbles and inspires all at once. The abyss doesn't care whether we understand it or not. It will keep breathing, glowing and shifting long after we're gone. But in the act of seeking it, of sending our lights and questions into its darkness, we do something profoundly human. We acknowledge the limits of what we know and reach beyond them anyway. The ocean, in its endless depth, becomes a kind of truth, that mystery isn't meant to be conquered, only met with wonder. And that sometimes the most meaningful discoveries are not the answers we find, but the questions that keep us diving back into the dark. The journey upward is slow and gentle. The darkness softens, the pressure lightens, and the blue begins to return. Faint at first, then blooming quietly through the water. After so long in the abyss, the shimmer of daylight feels almost unreal, as though the world above had been waiting patiently for us to come back. As we rise, it's hard not to think about what we've seen, how fragile life is, and yet how endlessly determined. From glowing worms to giants of muscle and eye, from volcanic fire to the silence of the deep. Every form we've met is a reminder that life doesn't ask for comfort. It only asks for the chance to exist in whatever way it can. The ocean holds that truth with quiet grace. It hides its wonders not out of cruelty, but out of patience, as if to say that some mysteries are meant to be discovered slowly. And so, as we return to the surface, to air, to light, to sound, let's keep a little of that stillness with us. A breath of the deep, a moment of wonder. Thank you for listening. Rest well. Good night.